In this video lesson, I'm going to talk about symmetries, and I'm also going to talk about a tiling theorem. This will cover sections 11.2 and 11.3. First of all, this problem is very similar to what you will face on your next exam. It says to describe all the symmetries of some of these company logos. Now, some of these company logos do not have any symmetry, and I'll explain why. For instance, if you look at the BMW logo, because of the BMW not being repeated down here, it does not have any symmetry whatsoever. But let's look at the CBS logo, the I, right here. Notice it has horizontal reflective symmetry. It also has vertical reflective symmetry, but it does not have diagonal reflective. So it has horizontal and vertical reflective symmetry. Okay, next, this logo is going to also have what we call rotational symmetry. If you look at this, If you look at this logo, if we put a center of rotation in the very middle and we move this 180 degrees, it's going to match itself. Therefore, it has what we call point symmetry, which is the same thing as 180 degree rotational symmetry. So it has point rotational symmetry. So it has three types of symmetry, no more. Let's look at the Mercedes-Benz below it. The Mercedes-Benz logo has a vertical reflective symmetry. But it does not have horizontal. But it does have a diagonal reflective symmetry. Okay. Now, the other thing that it has is a rotational symmetry. Let's talk about putting our center of rotation. Now, notice we're going to go from point at the top to this point, and there happens to be 3 points alike on this circle. So, if you divide 360 degrees by 3, you get that this has 120 degree rotational symmetry. And that is how you define the rotational symmetry for the Mercedes-Benz. Let me see if there's another good example on this. Yes, let's look at the target symbol. The target symbol, notice, is a concentric circles. It has what we call circular symmetry. Whenever you can rotate any degree measure and it's going to match, we call that circular rotational symmetry. It does not have point symmetry. It does not have the others because it has circular symmetry. So it doesn't have the other types of rotational symmetry if it has circular symmetry. We always defined the rotational symmetry by the smallest degree that you can turn an object or rotate an object to match itself. It also has vertical and horizontal and diagonal reflective symmetry. So it's got horizontal, vertical, and diagonal reflective symmetry. Okay, so it's got lots of symmetry there. The Texaco symbol down here has vertical symmetry, but not horizontal and not diagonal because of the T. It doesn't even have rotational symmetry because of the T. That pretty much does it for covering symmetries that I wanted to cover. Let me go to this in section 11.3. I wanted to talk about this theorem because it's an important one, I think, to know from section 11.3. When you are going to tile a floor, and heaven knows we all have to tile our floors, what can we do an irregular tiling with? Well, here's the theorem. We can tile a floor with any triangular tile. It will work. That means any three-sided tile, you can do a tiling with it. Any four-sided tile, a quadrangular is a four-sided tile. You can do it whether it's convex or not. We have an example here of a five-sided tile. This is an example of pentagonal tiles. However, You cannot do it with a regular pentagon. It has to be a pentagon that has two parallel sides. Otherwise, you won't be able to tile a floor with it. There are certain hexagons that you can tile a floor with. Of course, a regular hexagon works. We've seen that on all of our HGTV shows. Okay? But the rule is that for hexagons that are going to tile a floor, they have to have two opposite parallel sides of the same length in order to be useful for tiling a floor. If you tried to tile a floor with an octagon, it wouldn't work. If you tried to do it with a septagon, or even a 9 or 10-sided tile, it wouldn't work. These are the only 4 tiles that are going to work. So just keep that in mind, and I think that's an important theorem to know.